Previously, we covered the core foundations. Now in part 2, we tackle Deimos, science value and comparison to Phobos. Last time, we introduced Deimos, the smaller, quieter of Mars's two moons, sitting further out in a near-perfect circular orbit. That quiet, unremarkable appearance is exactly what makes this episode's question so interesting. What does Deimos actually tell us scientifically, and how does it stack up against Phobos, its larger, stranger sibling? Both questions matter more right now than they might seem, because several space agencies are actively planning missions to the Mars system, and which moon you visit first depends entirely on what you think each one is worth. Let's work through it properly. Deimos orbits Mars at an average distance of around 23,460 kilometers from the planet's center. Phobos, by contrast, sits at just 9,376 kilometers. The gap is immediate and striking. Phobos is close, dangerously close, geologically speaking. Deimos is comparatively comfortable. In terms of size, Deimos is small, even by moon standards. Its average radius is about 6.2 kilometers, making it one of the smallest known moons in the solar system. It's not spherical either. Lumpy, roughly triaxial, with dimensions of approximately 15 by 12 by 11 kilometers. Phobos is larger, around 11 kilometers in average radius, but both are tiny objects by any planetary measure. The orbital geometry matters quite a bit here. Deimos completes one orbit of Mars every 30 hours and 18 minutes, moving in the same direction Mars rotates, but just slightly slower than the planet spins beneath it. Standing on Mars, you'd see Deimos rise in the east and set in the west, like the sun, only very slowly. It would take about 2.5 Martian days to cross the sky. Phobos behaves entirely differently. It's so close and moving so fast that it rises in the west and sets in the east, completing more than 2 full orbits every Martian day. That difference isn't just a visual curiosity. It has real physical consequences for the long-term fate of both moons, though we'll come back to that. The surface of Deimos differs from Phobos in one striking way. It looks smoother, not because it has no craters. It does. Swift and Voltaire are the two largest named ones, and both are clearly visible in existing imagery. But the terrain between them appears softened, blanketed in loose regolith, fine, fragmented material that's gradually filled in smaller features over time. The working explanation is that Deimos has just enough surface gravity to retain debris thrown up by impacts rather than losing it to space. Material falls back and settles, round after round, over billions of years. Phobos tells a different story. It's scarred, grooved, and heavily cratered, with Stickney, a crater nearly 10 kilometers across, dominating one face. The parallel groove systems are still debated. One leading hypothesis links them to tidal stress from Mars's gravity, which is slowly pulling Phobos inward. Another connects them to the original Stickney impact. Neither explanation has been conclusively settled. Neither moon has an atmosphere in any meaningful sense. Deimos may have the thinnest of transient exospheres, an extremely sparse, loosely bound cloud of particles close to the surface, kicked up by solar wind and micrometeorite impacts, barely detectable and not permanent. Surface temperatures swing enormously as a result, around 0 degrees Celsius at the subsolar point, dropping to roughly minus 140 on the night side. With no atmosphere to distribute or retain heat, what you get is raw exposure. Deimos sits at roughly the same distance from the Sun as Mars, about 228 million kilometers, or 1.52 astronomical units. So solar heating is modest to begin with. Now here's where the comparison becomes genuinely interesting, and where the science gets more contentious. What are these moons actually made of? Spectral observations, measurements of how the surface reflects light at different wavelengths show a broadly similar picture for both. Both are very dark, with low albedo. Both have spectra described as featureless or flat across the visible and near-infrared range. That has led to comparisons with two asteroid types, D types, which are dark, and thought to be rich in organic material from the outer solar system, and the rarer T types. Neither matches clean. The spectra fit loosely, but don't map precisely onto any asteroid class we know well. That ambiguity feeds directly into the biggest open question about these moons. Where did they come from? Three serious hypotheses are on the table. First, they're captured asteroids, material from the outer asteroid belt, or perhaps further still, that was swept into Martian orbit early in the solar system's history. Second, they formed from debris ejected by a large impact on Mars itself, somewhat analogous to how Earth's moon is thought to have formed. Third, some variation or combination of both. The capture hypothesis has a real orbital mechanics problem. Getting two separate objects into nearly circular, near-equatorial orbits by capture alone is extremely unlikely, without some mechanism to circularize the orbits afterwards. The impact origin hypothesis handles the orbital geometry more naturally, but requires quite specific conditions during Mars's early history. A sample from Deimos, or detailed compositional data from orbit, could help distinguish between these scenarios. Interior composition, not just surface mineralogy, would be the key. And we don't have that yet. So how does Deimos' scientific value actually compare to Phobos? Phobos has received more attention, and for practical reasons. Larger, closer to Mars, and more accessible from certain mission profiles, it's also scientifically urgent in a way Deimos isn't. Mars's gravity is pulling Phobos inward at roughly 2 centimeters per year. In somewhere between 30 and 50 million years, it will either break apart into a ring or collide with the planet. That gives Phobos the character of a ticking clock, a geological process you can measure in real time. Deimos is moving in the opposite direction. At its distance, the tidal interaction with Mars nudges it slowly outward over geological time. It's in a stable, long-lived situation with no equivalent deadline. For mission planners, that stability is actually an advantage. Deimos sits further from Mars's gravity well, which makes it easier to enter orbit around without expensive fuel burns. A spacecraft approaching Deimos has more room to maneuver, and the radiation environment, while still present, is slightly less harsh than close to Mars near Phobos. JAXA's MMX mission, the Martian Moon's exploration, is the most developed attempt to address this directly. Designed to visit both moons, with primary focus on Phobos for sample return, it includes Deimos as part of the scientific program. If the Phobos sample shows composition consistent with carbonaceous chondrite meteorites, the captured asteroid hypothesis gains support. Material resembling Martian crust would point toward an impact origin. Deimos matters as a cross-reference. Shared origin should mean a family resemblance in composition. Genuine differences, not just superficial ones, would suggest the Mars system acquired its moons through more than one process. That comparison is scientifically valuable precisely because we don't have the answer yet. There's one more aspect worth drawing out, touching on the human exploration picture. Deimos has been proposed as a staging point for early crewed missions to the Mars system. A crew could enter orbit there, study both moons at close range, and operate robotic systems on Mars's surface via remote control with very low signal latency, just a few light milliseconds, without committing to the full risk and cost of a surface landing. This isn't a settled mission architecture. It remains a concept rather than a program. But it illustrates that Deimos isn't only a scientific target. Its position makes it a practical asset. Phobos has attracted similar proposals, but its proximity to Mars makes the orbital mechanics harder to work with. Deimos' easier approach gives it an edge in certain planning scenarios. Neither moon has been visited by a dedicated mission. Mars Reconnaissance Orbiter, Mars Express, and others have imaged both from a distance, but detailed surface science requires getting much closer. The most developed plan, with real mission infrastructure behind it, remains MMX, targeting a launch window in the late 2020s. Stepping back, what you're left with is two moons that look broadly similar, in surface darkness, in size class, in general appearance, but differ in orbital dynamics, surface texture, long-term fate, and the specific questions they raise. Phobos is urgent, dramatic, and heading toward destruction. Deimos is stable, smooth, and quietly posing a question we haven't yet answered. Where did it come from? And is the answer the same as for its sibling? Those questions will shape how we think about the early solar system, the history of Mars, and where we go next. Next episode, Part 3, looks at what it would actually take to land on Deimos, the mission design challenges, the surface conditions, and what we'd be trying to find out. If you found this useful, subscribing means you won't miss the rest of the series. The full Deimos playlist covers everything from the basics through to mission planning, and it's all linked below. That is part 2 of Deimos. Subscribe so you do not miss it.